in person, geometers, and yeah, so this will be an introductory talk about non-commutative topology and geometry. And actually in my talk, I will mostly focus on non-commutative topology, and then the second part, there will be more geometry. If by geometry you mean measuring distances, like the Greek word says. So, okay, here will be really a topological talk mostly, apart from the very last minutes. This is, I've just decided to start with this quote by Sophie Germain. That is something I really liked when I was studying, so well, 15, 20 years ago. This idea that algebra is written geometry and geometry is figured algebra. So this is the whole idea behind the algebra geometric duality that we see in many other fields of mathematics, not only in non-commutative geometry. So it's this idea that goes back to Descartes, that you can, if you want to describe geometric objects in the plane, for instance, you can associate to them equations and look at the properties of those objects by looking at corresponding algebraic properties. And this, of course, is the elementary version, and then that we also do in school. And this was brought forward by mathematicians all over the history of geometry. So in the early 20th century, by the work of Noether and Hilbert, with the various results about polynomials and their zero sets. And then later, this idea of using algebra to describe geometric objects and vice versa was even brought forward by Grothendieck when he restructured the whole algebraic geometry landscape. So somehow non-commutative geometry fits a bit inside this philosophy that you can describe geometric objects using algebraic properties. But the type of algebra that we are interested in is more analytic. It's a field that it's called operator algebras, and it has to do with algebras of operators on Hilbert spaces. So non-commutative geometry is often seen as a general mathematical framework that was introduced by Kohn in the 80s. So Kohn was an analyst more than anything else. At the beginning, he worked on von Neumann algebras, so which are a particular class of algebras of operators on Hilbert spaces. And the motivation for introducing this framework lies, well, in the theory of C-star algebras, but also in index theory. We will see a bit more of index theory in the second half of this seminar. There won't be any index theory in my talk. And the other inspiring motivation for studying non-commutative geometry, so for studying non-commutative algebras, is of course the non-commutativity of quantum theory. So the fact that in order to describe the quantum mechanical systems, you need to deal with operators that do not commute with each other. What I put here is some lines of the so-called non-commutative geometry dictionary, and this will be somehow the leitmotif of my talk. So we will try to understand what this dictionary has to say about this side of the word, so topology. So what do operator algebras tell us about topology? And in particular, we will focus on the first two lines. So we will first describe how commutative C-star algebras correspond to locally compact Hausdorff spaces, and then how finitely generated projective modules over commutative C-star algebras, well, unital, we will see, correspond to vector bundles, which is another geometric concept, or rather topological, I would say. And then we will briefly have a glimpse inside this word of how to describe manifolds. So when you put an extra structure using the framework of spectral triples, and this will be expanded on in the second part of the presentation. And I also put another thing that we may not really touch upon, but this idea that also the whole world of compact Lie groups admits an operator algebraic and algebraic version, which is that of compact quantum groups, and this can also be under suitable assumptions. So the non-compactness can also be dealt with, but for now, I thought this is enough motivation. So some oh, these are, oh yeah, I realize now that I swapped the last two lines. I'm very sorry for this. Yeah, I will fix it if you need the slides. So sorry. So these are the operator algebraic concepts, spectral tuple and compact quantum groups, and these are underlying geometric objects that you should have in mind when, yeah. So let's go. So as I said, the motivation behind non-commutative geometry is this idea of duality between algebra and geometry. And somehow in non-commutative geometry, the duality is a bit different because it's between topology and operator algebras. So let me start with explaining what this topological duality, which is known as Gelfand duality, entails. So if you consider a compact Hausdorff space, you can look at the collection of continuous functions on that space with complex values. And this is a set, but it's not only a set, it has a lot of extra structure. It will turn out to be what we call a C-star algebra. So to begin with, this set C of X as a vector space structure, meaning that you can take linear combinations of functions. And the way to do it is to do it pointwise. So if f and g are continuous functions on X and lambda is a complex parameter, then you can make sense of the function lambda f plus g. And this is the function that in the point X takes the value lambda times f of X plus g of X. So this is a extension of the vector space structure that C has by using pointwise evaluation of functions. In the same way, you can define a product between functions. This is, again, a pointwise product. This gives you a commutative product. So for every two functions that are continuous with complex values, you can define the product function fg to be the function that in the point X has the value f of X times g of X. If X is compact, then the function that is everywhere equal to 1 is a continuous function. And then this is there will be the unit with respect to this commutative product because it doesn't affect the product at all. And then there is a further structure, algebraic structure, which is an involution. And this is an involution that you get from the complex conjugation in the complex numbers. So for every function, you define function f star to be the function that in the point X has the value f of X complex conjugate. This is purely algebraic. It gives and there is compatibility between the vector space structure and the commutative product. So it turns out that this set C of X actually is what is called commutative star algebra, unital commutative star algebra. Then the analysis comes into place. So we can put a norm on this algebra, and this norm is given by the sup norm. So by looking at the supremum of all the values that the function obtains. Here X is compact, so it would actually be max. But the reason why I wrote it like that, it's because it's more suitable for generalization. And with respect to this norm, C of X is a Banach star algebra, meaning that it's an algebra with a norm and it is complete with respect to the topology induced by the norm. Moreover, this norm satisfies a very interesting property that connects all the structures that I just introduced to you. So this identity puts together the product structure, the adjoint, and the norm, and tells you that when you look at the norm of f star f, this is precisely equal to the norm of f squared. And this is actually what you have in the complex numbers, but you may not have it in general in an abstract Banach star algebra. There are many examples of Banach star algebras where this is not satisfied. So one direction, the one like this, is always there because you have the compatibility of the norm with the multiplication. It's a submultiplicative, but the other way around is non-trivial, and there are several examples. So being so special, this identity has deserved its own name, and it's called the C-star identity, and C of X then is a commutative C-star algebra. So C-star algebras are among the Banach star algebras, the one that have this extra condition that may not be trivial. So, and to show you how the C-star identity is really important, let's look at a very simple topological space. We just have n points. Then if we look at continuous, this is a discrete topological space that consists of n disjoint points. So when we look at the continuous functions on that space, we get C to the power n, the vector space Cn. And we know that this has a vector space structure. It also has an algebra structure, but in order for it to become a sister algebra, we need to choose a right norm. So if you would put the L2 norm, let's say the norm of the square norm, that wouldn't work. So the actual norm that you have to put there is the maximum norm, because it's the one actually that we wrote there, it's the supremum. So if you have an n tuple of vectors, then the square norm is the maximum of the norm of the single entries. And this is very different than the square norm. And that's the norm that makes C of n a sister algebra. So with other norms, it's not a sister algebra, it's a Banach algebra. And if you think about what we're doing here, actually, is that we're seeing this n tuples of operator as a diagonal matrix with entries, these vectors on the diagonal, and what we're taking is the operator norm of that matrix. Okay. Now, this Gelfand duality is, so far we have started from a topological space and we have constructed a sister algebra. But the whole idea of this duality is that we want to go the other way around. So from a commutative sister algebra, we would like to be able to construct a topological space. And this is indeed possible because any point in your space can be seen as a functional on the algebra C of x. And this is done by considering evaluation. So it's a functional, so it's a map from C of x with values in the complex numbers. And if you take a function f, sigma p applied to f is just the evaluation of the function in that point p. Now this the function of sigma p for a fixed p satisfies this property that when it's multiplicative, meaning that when you apply to f of g, it's a product of the functionals applied to the function separately. And this comes from the fact that the product of fg evaluated in p is the pointwise product of the values, so you can obtain this. Moreover, it has value 1 on the identity function, and this we call a character in mathematics in analysis, or also a pure state if you're more motivated by physics and quantum mechanics. And the important result is that all the characters on the commutative sister algebras of the form C of x are of these forms, and you can prove that the set of character sigma of C of x, so the noted sigma of C of x, is actually homomorphic to the starting topological space. So this is good news because it means that if you start from a sister algebra and you look at the set of characters, you do get a topological space, and this space recovers the underlying topological space of your algebra of functions. And it's not only, so this is actually the main, so it's homomorphic, and you can also get this theorem that is due to Gelfand, that whenever you have a commutative and unital sister algebra, yes?
So the space you obtain from algebra is always a compact
algebra? Yes, if the algebra is unital, it's always a compact Hausdorff space. Yeah, so this pure states also separate points. I'm not going into the details of that, but this character separate points, so to give you the Hausdorff property, and then
it looks a little bit like Stone's theorem.
Exactly, yeah, the Stone-Weierstrass, yeah, follows from that. And so whenever you have a commutative unitar sister algebra, you can look that you don't know whether it's of the form C of x, but you have some abstract sister algebras that is commutative, and then you can look at the characters on these commutative sister algebras. This gives you a topological space, which is Hausdorff and compact. And then actually you have a star isomorphism. So you're respecting all the structures between the algebra and the continuous function on the spectrum of that algebra. So you can go also the other way around.
Just next time that there's a question, can you maybe repeat it?
Oh, yes, sure. Yeah. Yeah, so the question was about the topology of this space. Well, it's compact in Hausdorff. Okay. And this idea, this star isomorphism actually goes even further. So you can prove that there is an equivalence of categories between the category of compact Hausdorff topological space with continuous maps and the category well, the opposite category, because this functor reverses all the arrows of commutative unit of sister algebra with star homomorphisms. And this could actually be extended beyond the compact world, but you need to take a different type of maps there. So let me go back to the dictionary. So this is what we were discussing. If you have a commutative sister algebra, it corresponds actually, as I said, you can drop the unitality assumptions. It corresponds to a locally compact Hausdorff space. You need to work a bit there. And you can show that whenever the sister algebra is unital, the underlying topological space is necessarily compact. And if whenever you do a process of unitization of a non-unital sister algebra, either by adjoining the unit or by taking different type of unitization, then this results in the topological world in compactifying your space, and different compactifications correspond to different unitization. So the minimal one is the 1-point compactification. The stone-checked compactification corresponds to taking the multiplier algebra, which is the biggest algebra possible. And there are all correspondences here also. So if you're, as I said, if you stay inside commutative sister algebras without requirement of unitality, then star homomorphism are actually continuous and proper functions. And this has to do with the fact that the underlying space is not compact anymore. So you need to add the properness condition. Then ideals in the algebra correspond to open subsets. And if this ideal is essential, which is a property, an algebraic property, then the corresponding set is dense. And of course, whenever you have a homomorphism of a topology of a sister algebra, because this, we have this functor and equivalence of categories, this will turn to give you a star automorphism of the algebra. So whenever you have, this also means that whenever you have an action on a topological space, you can turn it into a corresponding action by star automorphisms on the sister algebra. And then other notions like metrizability of your space correspond to other analytical properties like separability of the sister algebra. So it's really, because it's an equivalence of categories, you really can translate many topological conditions that you have on the side of your underlying topological space into corresponding conditions or operations on the side of the sister algebra. All right. Okay, so before I move to the next topic, are there questions? Comments?
How important is that we're looking at functions in C? Of course, you have this star, but if I look at real value functions.
Yeah, this you can do. There is notions of real sister algebras, but this you would get starting from a complex one and putting an involution and look at the fixed points for that involution. So you can be in the real category, but it's much more complicated than, I would say the analysis becomes also more complicated in the real. So there are notions of real sister algebras, and this is something you can work with. But yeah, of course, the star becomes a bit something you lose, but yeah, you can still do it. Bram, you look perplexed.
No, I'm just, I think Gelfand works.
Yeah, we just work.
Real value functions.
Yeah.
And yeah, your star just, it's not there in that case.
Yeah, but somehow
it's a real sister algebra.
The theory of a complex sister algebras is much more developed than the theory of real sister algebras. There is a theory of real sister algebras, and usually they are treated as fixed points under an involution on a complex sister algebra. So.
Yeah, and there are the usual advantages of being able to sometimes use analytic functions.
Yeah, exactly. So there is a whole exactly.
Such thing. I mean, C just has advantages. Okay, but you
yeah, there is also the holomorphic functional calculus that you have in sister algebras.
But you don't get like new things on the topological side or different things.
No.
Not really, not essentially. No.
Yes.
So you mentioned stone check compactification over there. So this duality also, I mean, to me looks a little bit like where you see stone duality for Boolean algebras.
Mm-hmm.
That's very similar correspondence. Is that related in this?
I think that would take you more into a von Neumann
Yes,
world.
I don't know what the precise relation is, but there is something like.
You mean this thing about functionals and measures?
No. So if you take ideals and Boolean prime ideals in Boolean algebra, and then look at open down sets.
Mhm.
You retrieve the algebra again. So it's a similar.
Yeah.
duality.
Yeah, so I think you can single out the Boolean spaces in this language by looking at C-star algebras that are close to undertaking supreme in a certain ordering.
Oh, yeah.
So you can characterize that
Right.
That's
as
true.
well, yeah. But it's a subclass.
Sure.
Yeah, and then here there's also a correspondence between ideals and how do you say functional.
Mhm.
So there is a whole part that was not mentioned here, but thanks for asking. Oh yeah, I forgot to repeat the question again. Sorry, Thomas.
I'll type a summary.
Okay. Okay. So the other part in the dictionary was the connection between modules and fiber bundles. So I should also say modules and vector bundles. That will be the only part that I will focus on today. So I'll just recall some basic notions from the theory of modules over algebras. So there's no analysis here yet. So whenever you have a complex algebra, there is a notion of right modules. So that's a vector space with a right action that respects all the structure of a vector space that your module has. And so we're interested in right modules here. And if you have a family of elements that satisfy this condition here, which means that you can just decompose any element in the module as a finite sum of a linear combination with coefficients in the algebra of these elements, this selected family, then you say that this family is a generating set for the module. And it's important to know that generating sets may not be unique, and the expression also may not be unique. Then a family of this form is called a free family if actually the elements of the family are linearly independent. And it is, oh my God, another typo. A basis, oh no, it's just a space missing. A basis is a free generating set, meaning that it's a generating set such that every element can be written then uniquely with one expression of this form. So we say that the module has a basis if it admits a generating set that is also free, so such that its elements are linearly independent. And then we call a module is called free itself if it admits a basis, and it's called algebraically finitely generated if it admits a generating set that is finite. And this is a so from now on, we assume that A is a unit of star algebra, so we don't put any norm on it yet. And then we can consider the module A to the power n, which is given by the direct sum of the algebra A with itself n times, so it's just a direct sum module. This is free, it's finitely generated in a very simple way. You just take the collection of vectors which have 1 in the first entry and 0 otherwise. And then because the module is A to the power n, you can use the 1 to multiply and generate everything you need. And this is a basis called the standard basis of this free module again. So if a module is finitely generated, meaning that it emits a finite generating set, then you can always find a positive integer and a surjection from the module A to the power n into your module, such that when you apply this surjection to the elements of the standard basis of AN, then you get a generating set on the other side for your module. And finally, a right module is said to be projective if it can be realized as a direct sum of a free module of the type A to the power n. And this means that there exists a free module and a module E prime such that E plus E prime is actually equal to this free module. This is an isomorphism of right modules. Yeah, well, I have an example now. I don't know if it's the standard one. Will come in a second. So the motivation for this is this example. So if you have a vector bundle over a compact Hausdorff space, which means that you have a locally trivial family of finite dimensional vector spaces that are indexed by under your base space, then you can look at the sections of the complex vector of these complex vector bundles. This space of section is denoted gamma E in the literature, and this is a module over the algebra of continuous functions on the underlying base space. And the multiplication is just a pointwise multiplication. So if you have a section and a function, then the value, you get a new section whose value in the point x is the product of the value of the section and the function that you're multiplying from the right. And this gives you a structure of, as we will see, it gives a structure of a right module over C of x, but it will also be an example of this finitely generated projective modules. So what is interesting about this gamma, this is called a gamma functor, is that it actually respects a lot of the structure that you have in the theory of vector bundles. So first of all, if you have a bundle map, so a map between E to any prime that's, well, bundle map, so it's in the category of vector bundles, then there exists a map at the level of the corresponding modules that goes the same way, and it's given by just the composition of the bundle map with the section question. And this map is linear with respect to C of x, because this is linear in each fiber. So when you restrict this map to the fibers of your vector bundle, you see that this map respects a linear structure that you have in these vector spaces. So actually the correspondence that to a complex vector bundle over a compact topological space associates the modulus of sections of the vector bundle is a functor from the category of complex vector bundles over X to the category of C of X modules. And this functor actually respects, as said, several algebraic and topological structures that you have on bundles. So if you look at the module of section on the dual bundle, that's actually the module, the dual module to gamma E. So it's home with respect to C of X from gamma E to C of X. It also respects direct sums of vector bundles. So the direct sum of the modules of two vector bundles is isomorphic to the modular section of the direct sum vector bundle. And it also respects the tensor product of bundles, meaning, and this is a balanced tensor product over the algebra of functions on the base space. And the reason why this tensor product that I wrote here on the left side makes sense is that, well, in principle, gamma E and gamma E prime are both right modules, but because everything is commutative here, or rather we say they're central, C of X bimodules, the multiplication can be moved both sides, and this balanced tensor product makes sense. So this is something that when you drop commutativity needs to be taken care of. Okay, so the main result is that whenever you have a complex vector bundle over X, then the module of sections gamma V is finitely generated and projective. And this in particular means that you can find an idempotent in a matrix algebra over C of X for some n. The n may not be related at all to the rank of your vector bundle. It's more related to finding a partition of unity for the underlying compact topological space. And you're able then to realize these modules of sections and as the image of an idempotent applied to the module C of X to the power n, which was this free module that I introduced earlier. And modules that are images of idempotents applied to free module are finitely generated and projective. And conversely, and this is the more complicated direction of in the theorem, if you have a Cx module of the form E Cx to the power n, so which is finitely generated and projective, then it must necessarily be the module of section of some vector bundle over the spectrum of that algebra. So in particular, the gamma functor from vector bundles over compact topological space into the category of finitely generated projective modules over the corresponding algebra of functions is an equivalence of categories. And maybe and this is somehow the extension of the equivalence of categories that you have between X and C of X between topological spaces and sister algebras. This is now extended to vector bundles, but of course here you're fixing the underlying topological space, or if you want, you're fixing the algebra. And this is only in the compact case. So the unitality assumption is essential here because you need to make sense of free modules and of being finitely generated and projected.
So there's a something maybe that we have everything Hausdorff, or
Yeah, so we're still in the Hausdorff, compact Hausdorff topology, and plus the compactness is important here. Yeah. Okay. So somehow summing up in this first part of this talk, we kind of made sense of the first two lines that I presented. So there is a correspondence between the operator algebraic concept of a commutative sister algebra and the topological concept of a locally compact Hausdorff space. And if you restrict to the unital case, finitely generated projective modules are really correspond in an equivalence of category way to vector bundles over compact topological spaces. So the whole idea of non-commutative geometry is, well, as I showed you here, you can translate several concepts, and the same you can do at the level of vector bundles. So in principle, you could extend the notion of K-theory, which is this homology theory for topological spaces defined via vector bundles, can be extended to operator algebras by looking at finitely generated projective modules over sister algebras. So the whole idea is that of non-commutative geometry, as we understand it now, or rather non-commutative topology, is because there are these dualities. When we look at the sister algebra, they may not be commutative. We may think of that as some algebra function on some virtual topological space. This sounds a bit philosophical, and it is also, I would say. But so we wonder whether by looking at algebras that are not commutative anymore, we can still make sense of several topological concepts that are out there for their commutative counterparts.
When you think of this underlying space, if you like, the X, that's the same in all examples. Or
well, for any X, you have a commutative sister algebra.
right. And for any X, you have your vector bundle.
And for every, and if you fix X, you have vector bundles on X, and those correspond to modules on C of X. So here you have to fix X, but above it's just any X gives you a sister algebra. And for each of those, you can do this correspondence regarding vector bundles. Okay, so now, because of this analogy, I would like to talk a bit about examples of non-commutative sister algebras and what they can do for you. I will consider some very basic examples just to give you an idea of what kind of objects we encounter. But before that, I have to give you the definition of a sister algebra. So we just dropped the commutativity that we saw so far. Sister algebra is a Banach star algebra. So it's an algebra with a star. This involution is incompatible with the algebraic structure, and there is a norm with respect to which A is complete. And this norm satisfies this identity, A star A is equal to A squared. And as said, this may not be the case in arbitrary Banach star algebras, and makes sister algebras actually much more easy to handle than general Banach algebras. So a natural example is the algebra of n by n complex matrices. This has all the structure that you want, but then of course now comes the norm, and that's the important part. The norm that you have to consider to have the sister identity is the supremum norm, or if you want the operator norm. So you define the norm of A to be the supremum of the norms of the vectors that you obtain by applying A to vectors of norm 1. So this is not the max. This is not the L2 norm. This is not the highest, necessarily the highest eigenvalue norm. It's really the operator norm of that matrix. Right. This is the highest eigenvalue norm. Sorry, I wanted to say, yeah.
It's the largest singular value.
Yeah, exactly. So this is the highest. Sorry, I misspoke myself. So you could put other norms of this algebra, but the one that you get is really the one that gives you the max or the sup over. So, and if you want to, this is the operator norm indeed, and this can be extended to finite dimensional spaces. So the algebra of bounded operators on a Hilbert space, which again is a natural adjoint that comes from the inner product in the Hilbert space. And as an operator norm is also a sister algebra. So you also have the sister identity there. Again, the operator norm is defined likewise by looking at the supremum over all vectors of norm 1. And then inside this algebra of bounded operators on Hilbert space with sister algebra, you have an ideal. It's ideal of compact operators, and this is also a sister algebra. So these are all examples of non-commutative sister algebras. In the matrix case, if n is equal to 1, you get the complex number. So that's the only commutative one.
But that's a highly non-constructive proof.
Yeah, I'm not proving anything. Yeah.
I did this as in 1982 or 3 for my graduation project, this theorem.
Yeah.
And it involves the construction of a big Hilbert space as the product of many other things, which is really full of Zorn and everything.
Yeah. It is
the space you get is not optimal.
No, it's not optimal. No, you get things that are.
Yeah.
So okay, so I said this B of H is a prototypical example of sister algebra because of this theorem, the Gelfand GNS construction. So whenever you have a sister algebra, you can always find a Hilbert space and an injective star homomorphism from that algebra into B of H for that Hilbert space, which means that you can push any sister algebra faithfully inside an algebra of operators. But I said this, well, somehow it is constructive, but it's not optimal. So this, you can construct quite explicitly what the Hilbert space is, but yeah, I mean, then you have to define a norm using a suprema, and it's not a great, well, it's not very workable with.
When is the Hilbert space separable? That's something that can be answered.
I think if the
algebra is separable,
then
then
you can
B of
find
H
it
is
even
separable,
represented
yeah.
as separable Hilbert space.
Ah, okay.
Yeah.
So in that sense, stay in a small sort of reasonable setting, but in general, you need to prove that there are enough states which are certain functionals with certain properties, and there
And
you
then you have
there you
this.
have the Zorn, yes, to get that.
Yeah. So it's and it's not optimal. Like in one example we will see in a second, if you would do the GNS construction there, you would really get a huge Hilbert space that doesn't do. There are much better candidates in most settings. But the whole idea is that all the sister algebras, commutative or not, can be represented in a less or more or less efficient way as algebras of operators on some Hilbert space. So this is the example that I had in mind. I will give you now a representation of the algebra of continuous functions on the circle on a suitable Hilbert space. This is not the GNS representation. That if you would apply the GNS representation there, you would get huge Hilbert space that doesn't really help with this. So we look at the topological space. This is the circle. So we look at points in the complex plane that have distance 1 from the origin. And then you can define a corresponding sister algebra. This is from if you want more algebraic flavor, you can think of it as a closure in the subnorm of the algebra of Laurent polynomials. And this algebra C of S1 can be represented on the Hilbert space L2 of S1 by multiplication operators. So just by multiplying a function, an L2 functions with a continuous function. Now this L2 of S1 is also through Fourier theory isomorphic to the little L2 of Z, so the two-sided sequences. And if you look at this isomorphism, the multiplication by e to the 2 pi I theta, so by the basis function in your Fourier series expansion, is actually mapped to an operator, which is called the bilateral shift. It takes the vector, the basis vector labeled by n, maps it to n+1, because you're adding another theta, basically, and the adjoint takes any basis vector to the previous one. And then you can say the C of S1 is the smallest C-star subalgebra of the bounded operator, so little L2 of Z, that contains this unitary operator U. And because it is unitary and there's only one generator, this is a commutative algebra. There's no other relation there, apart from U star U equal to U star equal to 1. Okay, so this is a commutative example, but then you can play a bit with it, change the example a little bit and get an interesting non-commutative example of sister algebra. And so if you look at the different Hilbert space, you use little L2 of n. so which via Fourier transform correspond to the Hardy space. Then you get the shift operator, and this is defined likewise. So it just goes up from the n basis vector, gives you the n+1 basis vector. But this is clearly not invertible. This is an operator whose adjoint, it's clearly not invertible because you can only go down until you reach the vacuum vector. And then you can do the same trick, define an algebra called the Toeplitz algebra in this case, as the algebra of operator inside B of this Hilbert space that contains operators like T and all its powers and adjoints. And this algebra is clearly non-commutative because while T star T is equal to the identity, when you do it the other way around, you just get the identity up to minus the projection onto the vacuum vector. And this is one of the simplest examples of non-commutative C-star algebras that you can think of. It has one generator. And what is nice is that this property that I wrote, the T star T minus TT star are, well, is not zero. This projection tells you that the elements of T commute up to compact operators because T commutes with this star up to a rank 1 operator. And when you do all powers, you can prove that this is up to compact. And this gives you a nice, well, in my opinion, very nice extension of C-star algebras that shows you that you can realize commutative C-star algebras as quotients of two non-commutative ones, for instance. And it's interesting because in non-commutative geometry, we think of extensions of this form as boundary extensions, meaning that the algebra that you get of a quotient can be thought of as a non-commutative boundary of some non-commutative algebra. And this analogy also works because if you look at the spectrum, so the set of pure states now of this non-commutative C-star algebra, then this gives you a disk. So you really have something that is, you have something here that is the boundary of the spectrum of the C-star algebra in the middle. And this is one of the simplest extensions of C-star algebra. It's also one of the building blocks of index theory. I don't know if it will appear in your talk, Bram.
Is in some form.
Yeah. So maybe more on that will follow in.
Maybe not as this.
No, but you will have some index, right?
Yeah.
Okay.
This concept of commutation, modular compact perturbations.
Yeah.
That's a fundamental concept in this.
Yes.
Yes. Yeah.
Yes. This I will also say something about.
I mean, index theory, it's
Yeah.
Also invertibility up to compacts and yeah.
So compacts are viewed as infinitesimals somehow.
In non-commutative geometry. Yeah. Okay, so this was to show you how a commutative C-star algebra can be realized as a quotient of two non-commutative ones. The other example that I have, well, this is purely commutative, then we move to a non-commutative setting, is the commutative and the non-commutative tori. I will focus on dimension 2. So if you go one dimension up here and instead of considering the circle, we look at the two-dimensional torus, then again, we have Fourier theory that helps us, and we can consider the algebra C of T with basis functions e to the 2 pi I x, e to the 2 pi I y, and do a Fourier, for every continuous function, we can write a Fourier series expansions. It's a doubly indexed sum over the integers. These may or may not converge. In general, they don't. And but if we restrict to a dense subalgebra of this, the C infinity of T, then we do have some convergence. Actually, the best would be to restrict yourself to Schwarz functions. But already for C infinity of T, you have that this coefficients here that appear in the Fourier series expansion satisfy some bound condition. So meaning that for every K, you have the supremum of the power of the products of 1 plus m squared plus n squared to the power K times the square norm of the coefficients is always bounded. So this is the rapid decay of Fourier coefficients, resulting Fourier analysis. And this will be our motivation for defining two algebras, two non-commutative algebras, mimicking what happens when you look at the functions on the commutative torus. So now comes a non-commutative algebra. This is called.
Sorry, this story about this convergence also popped up in a circle.
I didn't really mention their convergence, but yeah, of course, if you do a Fourier series expansion of a continuous function on the circle, you have the same problem, that they may not converge to the original one. But if you look at smooth functions, then you do have convergence. Yes, so now we define a different sister algebra. This algebra is called the rotation algebra. Sometimes it's also called the non-commutative torus. We fix a parameter in R, eventually will be between 0 and 1. And we define the rotation algebra as a sister algebra generated now by two unitaries. So meaning that U star U is equal to U star is equal to 1. And the same is true for V on some Hilbert space that satisfies some additional condition, which is that they commute up to a phase, and this phase contains this parameter. So for every theta in R, we get a sister algebra. There are some observations that are at place here. If you look at e to the 2 pi I equal to theta, sorry, e to the 2 pi I theta is equal to 1, meaning that you have then that theta is a multiple of an integer. Then everything here is commutative because your phase factor is 1.
This is a different kind of up to than we just.
Yeah. This is a different one. This is just this is a different type of commutation relation also. So you just have two generators and they don't commute. There is a phase. Whenever you multiply them, you get an extra phase that gets pulled in. Now, this relation that I wrote remains unchanged if you translate your theta by an integer, because the phase eats it up. So actually we can restrict our analysis to picking a parameter theta in 0 and 1. Actually, you could also restrict to 1/2 by playing swapping U and V, but let's just leave it between 0 and 1. This algebra is one of the first examples of non-commutative sister algebras that were studied also in use in applications of non-commutative geometry, including applications to solid state physics, but also to the theory of foliations. And it has a Mizar representation on L2 of T. So on this, T now is a two-dimensional torus. And we can construct two operators. The first operator is the unitary multiplication by this, that to each function associates the function defined by multiplication by e to the 2 pi I t. And then you have another operator, which is a translation operator, meaning that for every t in the torus, you just translate your function by that element. And when you try to see how these two operators interact on this Hilbert space L2 of t, you realize that they actually satisfy the commutation relation that I wrote before. So this is a concrete representation of this sister algebra on a quite natural Hilbert space. And then we write the elements of a 2 theta in the form of a power series expansion. And then this power series expansion is compatible with the involution, meaning that, oh, it should be a star here, I'm sorry, that A star is equal to the expansion that you get by complex conjugating and swapping the indices, inverting the inverses. Okay, so where does this algebra come from? Well, it could be seen as a mere non-commutative version of an algebra we know, which is C of T, but it actually has a motivation from dynamical systems. So what this algebra is representing is the action of the infinite cyclic group on the circle. And the reason why I put a two-dimensional picture will become transparent at the end of the presentation. So we take we define an action of the infinite cyclic group, which is generated by rotation by an angle theta. And so for every theta between 0 and 1, we define this action t theta of x is e to the 2 pi I theta x for every x in the circle. So we just take a point in the circle, rotate it by this angle theta, and then go on. And clearly there are different behaviors, whether theta is rational or not. If theta is rational, then eventually we go back to the point we started from, but so the orbit is periodic. It just consists of some collection of points. However, if your theta is irrational, then the orbit of any element under this action is dense, meaning that the orbit will never close. We will always move around in the circle and never get back to the point we started from. And now, because of the non-commutative geometry dictionary, this action of Z on S1 induces an action of Z onto the C-star algebra C of S1. And out of those ingredients, it's possible to construct an algebra that encodes the property of this dynamical system. This is called the cross product. I'm not going to explain how to construct it, but just to give you a motivation, this algebra will actually be generated by two unitaries. The first unitary is just the unitary that generates C of S1. And then there will be another operator, V, which is also unitary, and is the one that implements the action of Z on S1. And because this action is by rotation by theta, when you compose this U, V in different orders, this parameter theta will appear there too. This cross product sister algebra is indeed isomorphic to the universal algebra that I defined a couple of slides ago. And it's also equivalent in some sense to the algebra that you would get from studying this two-dimensional system known as the Kronecker foliation, where you do the similar thing. You get rotations by theta, but now inside the torus, and whether theta is rational or not, your orbit will close and give you a circle or be a dense orbit that winds around. So what can you do with this algebra? You can do a lot of things. You can look at the rapidly decreasing functions on this algebra, and these are defined by just saying that they're the functions that have coefficients that are Schwarz. If your theta is not rational, so if you're in the case of this very badly behaved dynamical system, then your algebra is a trace, and this trace gives you an inner product on the algebra, so it turns it into something that it's called a C-star module. And this trace, it turns it into a Hilbert space, I'm sorry. And then the coefficients in your Fourier expansions are actually Fourier coefficients, meaning that are obtained by looking at inner products of functions with generating basis elements. Okay, and another thing that you can do, and this is where we are starting to go towards the geometry world, is that we can define derivations on this algebra. So a derivation is on an algebra is just a map from the algebra to itself that satisfy the Leibniz rule. So the D such that DAV is dA times B plus A P of B. So we can define two derivations on the algebra of the non-commutative, on the smooth algebra of the non-commutative torus. We have a derivation in the direction of U. So delta 1 of U is 2 pi I U and delta 1 of V is 0. And delta 2 of V is 2 pi I V and delta 2 of U is equal to 0. So here I wrote some generic formulas, but to give you an understanding of what these two derivations are, you can look at what happens if you put your parameter theta equal to 0. So if you're on the smooth functions on a genuine torus, then what I'm saying is just that delta 1 is the partial derivative in the x direction, and delta 2 is the partial derivative in the y direction. But in fact, this can be extended to, this is not sensitive of theta. This just gives you u. If you apply delta 1 x only on u, delta 2 or x only on v, but there is no interplay between the two, and there is no theta appearing. And indeed, the two derivations commute, and they recover the partial derivatives that you would have classically. So why do we care about these two derivations? Well, you can put them together in a new operator which generalizes the Cauchy-Riemann operator. And the Cauchy-Riemann operator is that operator whose solutions give you the holomorphic functions. And you can define two Cauchy-Riemann operators, well, one and its conjugates on a non-commutative torus by just taking delta bar to be delta 1 plus I delta 2 and delta to be the one with the minus. So this operator is a differential operator on the algebra of the non-commutative torus. It has a kernels which are multiples of the identity. And then when you restrict to the kernel of this, of the trace, so the trace of the unique trace that this algebra has, then it's actually a bijection. And it's like it's really an analog, a non-commutative analog. It really doesn't see much of the of the non-commutative structure. There is no theta appearing here, but the spectrum really consists of complex numbers of the usual form. So it's the same spectrum as the Cauchy-Riemann operator. And this is not a coincidence. Algebras of this form, like non-commutative torus, are called isospectral deformations of commutative algebras. So when you look at certain types of differential operators, thereon you do get the same properties that you would get classically.
Sorry, can I ask a question? So
Yeah.
vector bundles were sort of thought of as these projected modules. And I guess these things are elements of the tangent model, right? These are sections of the tangent model. So the space of all these derivations forms the tangent. Do I think of that as the tangent space? And sections of the tangent space.
No, but you can't do it because there are many C-star algebras that do not admit any derivations.
Oh yeah, that's
so
true.
The fact that this one happens to have two derivations is somehow
special.
Coincidental. It says that it's quite close to being commutative still, in some sense.
Yeah, these are called almost commutative manifolds.
Yeah. And how much does this depend on theta? I mean, there's
Nothing.
a distinction. So they're all isomorphic? Like if
no,
theta
so the algebras are not all isomorphic, but the properties of these differential operators do not depend on theta. They're the same as if theta would be 0, but the algebras are pairwise non-isomorphic if theta is irrational. No, I think yes. And there is a notion of equivalence, which is called Morita equivalence. So if theta is in the orbit of a fractional linear transformation, then they have the same representation theory, the same K-theory, the same projective modules. So they share a lot, but they're not isomorphic. And again, there is a huge distinction between the ones for rational and the one for irrational. So the rational ones are all equivalent in this Morita equivalent sense to commutative tori, and the irrational ones are not, but they have some equivalence amongst themselves for different thetas. I don't know if you will mention Morita equivalence.
I will say something about it.
Yeah, so we can also do a order 2 operator on this non-commutative torus. This is a bit to motivate what will be discussed in the talk by Bram. So we can look at the analog of the Laplace operator, so delta 1 square plus delta 2 square. And this is again isospectral to the classical one. It is an operator on this smooth algebra inside the non-commutative torus. And the spectrum of this operator is just minus 4 pi square with this m squared plus n squared. So it's really the same spectrum that you would have for the classical Laplace operator. And again, like the Laplace operator, it has the same set of eigenfunctions, and like the Laplace operator, you can realize it says delta delta bar or delta bar delta. So somehow we see already here that delta and its conjugate are kind of square roots of the Laplacian, not exactly. So we can find the square root of the Laplacian by using polymatrices. This will be the Dirac type operator on the non-commutative torus. Again, here everything is, the domain is not functions, it's elements in an algebra. So there are no points, but we can still make the same construction that we would do classically when defining the Dirac operator on a manifold. So we take the Pauli matrices, going to 2 by 2 is enough here. We take the 2 by 2 Pauli matrices and we define the Dirac operator as a sum, well, as a linear combination of multiplications of our basic derivations with Pauli matrices. And this is this operator minus I 0 delta delta bar 0. This is a self-adjoint operator. And it acts now, it doesn't, on a Hilbert space, which is a Hilbert space that consists of 2 copies of the completion of the algebra A2 theta in the norm coming from the trace. And this operator is indeed a square root of the Laplacian. Well, it's two-dimensional square root of the Laplacian, meaning that when you square it, you get minus diagonal operator with the Laplacian on the diagonal. And this whole idea of finding square roots of Laplacians and looking at the Dirac operator, well, it's motivated mostly by index theory. This will be discussed in about half an hour. And this is an example of what is called a spectral triple on a non-commutative algebra, which is a construction of a Dirac operator that will give you geometric information about the algebra in question. And from which you can also do index theory computations and compute the invariance of such spaces. So I think it's a good time to stop and to summarize. So these non-commutative algebras that two of which I presented arise in a variety of mathematical settings. And in particular, if you look at sister algebras, they are very suitable to translate and to study problems that arise either in geometry or topology, and to give an interpretation of topological geometric properties in the sister algebraic setting. This you can do thanks to the non-commutative geometry dictionary, but thanks to this dictionary, you can also extend the study to situations in which you cannot really use geometry. For instance, when you study orbit spaces like the one that I showed you with the non-commutative torus, there is no orbit space when the rotation is irrational, but you can make sense of this setting by moving beyond non-commutativity, looking at a non-commutative object and trying to do geometry there. And to know a bit more on how to do geometry on such algebra, I think I refer you to the next talk. And thanks for being here and listening.
Thanks a lot. I found it very interesting. Are there any questions? We already have some questions. Maybe from the people joining from all over the world, or at least the rest of the Netherlands. For example. Maybe I have a question. So we have now this nice dictionary between these two worlds. So what's an example? Is there like some concrete example where you can say, well, here's a geometric or topological problem, and I can translate it in the C-star algebra language, and there the problem is very easy? Well,
very easy, I don't know, but I would say like this kind of orbit spaces for misbehaved, well, not well-behaved actions where the orbit space doesn't exist. You can replace the orbit space by the C-star algebras. And the reason for that is that if the action were well-behaved, so if it were free and proper, then you would, by constructing this kind of C-star algebras, like this non-commutative torus, you really get the orbit space up to some equivalence. So the idea is that in the situations in which I cannot define a quotient, I can look at a C-star algebra that contains the information about the action. And because there is this dictionary, you can compute topological invariants like K-theory. So you can actually associate invariants to that. And to go back to, again, both these non-commutative torus and this Toeplitz extensions are appearing also in applications to solid state physics, where you measure, for instance, the quantization of the Hall current in the quantum Hall effect. And the fact that this current is quantized is reflected through an index computed on this non-commutative torus. So it's also interesting because in the setting where you would expect to be working with bundles over classical torus in that case, in the solid state setting. But that doesn't explain the quantization that you observe in the laboratory. But if instead you replace the torus by a non-commutative one, and here the theta would represent the magnetic phase, then you do get a quantization into levels that reflects what you observe in the lab. So somehow it's by extending it beyond commutative algebras of functions to algebras of operators, you get to compute invariants that measure something that, especially in applications to quantum mechanics, are reflect the setting, the experimental setting, or correspond vaguely. Correspond more to the experimental setting than a genuine vector bundle would.
There's another question from chat. Nick asks, does a non-commutative C-star algebra correspond to a topological space with some non-commutative product?
No. So if it corresponded to a commutative space, then it would be a commutative C-star algebra. So,
but I could look at the space, for example, and look at matrices over C. Then I get automatically some other, but that's a completely different thing.
Yeah, that's a different thing, and also the spectra then become very different. So if you would do the spectrum construction on a matrix algebra, then it doesn't reflect the underlying.
Yeah, so that algebra doesn't have any known. So the matrix algebra is a good example. It doesn't have any non-trivial characters. It's simple.
Yeah, it's a spectrum.
So you really only have an algebra. There's no space you can associate and then recover the algebra by doing some trick, modifying a product. So there are many examples of C-star algebras that arise in from these, for example, these bad dynamical systems that have no ideals. So they're really simple.
Yes.
Yeah, so we heard, I mean, you came up with this example of solid state physics as a example, and I remember from a colleague long ago mentioning that it can be used for grand unified theory and all this. But what is like the simplest? What is the simplest physics example where it is non-commutative?
Well, I think
so we really want to have this language.
I
really want to have this.
I think that already, if you look at this, so there is this model for, it's called the SSH model, also in solid state physics, and it's about polymers. And there's there's this general principle in physics, which is called the bulk boundary correspondence, that some quantities that you can measure in the bulk of some material correspond to quantities that you measure on the boundary of the material. So sometimes it's insulating in the bulk and conducting on the boundary, for instance. And by looking at extensions of the type of this Toeplitz extension that I showed you before, this correspondence between the quantity that you measure, you can explain as an identity of classes in K-theory of two different C-star algebras. So somehow it's, especially, I don't know, there are other examples like in the standard model of particle physics, but I really think that one of the biggest success of with respect to application to physics is the fact that you can equal some quantities in the lab or relate the quantization of two different quantities in the laboratory by saying they're quantized because the indices of Fredholm operators are integers, and this is what we're measuring is an index. I think it's one of the most successful physical applications, but
it's not really so. It's a bit involved to describe distinct experiences. So even the two-dimensional quantum Hall effect.
Yeah.
That would maybe be the simplest example, but you would still need several boards to explain what's really going on.
But also for the quantum Hall effects, it's maybe it connects to this talk in the sense that what you're measuring are the Chern classes of non-commutative vector bundles on a non-commutative space, which is this non-commutative torus, and this torus has a family of finitely generated projective modules thereon, and if you measure their classes, they correspond to these levels of quantization in the current. So
Fabian comments, simple causal examples, periodic superstructures hosted by another periodic but incommensurable lattice.
Okay. That's also solid state, I would say, but I don't know if it's simple, simple example.
In the eyes of the beholder.
Yeah.
So thanks a lot. I think it's good to have a break.
Yes.
For those who are here, I have cookies. For those at home, get your own cookies. And maybe since it's now almost 3:15, I would propose that we take a half-an-hour break, if that's okay with everyone. Your mug is mine. So we'll start again according to form.
Okay, and am I still sharing? Oh yeah.
Yeah, so I was wondering.
Do you just want?
It's very nice to be here. It's actually my first visit to a Dutch university since arriving back in the country 2 years ago. But we all know what happened in between. So yeah, it's great to be here finally. I will continue this gentle introduction. I will warn that it might be slightly less gentle than the last talk. And I especially, of course, people online as well, but I especially encourage people in the local audience to ask questions or slow me down if I'm going too fast, or if you would like to see more comments on certain things. Yeah, so this is an outline. I will talk for quite a while about index theory and geometry in the manifold setting, because there will be a lot of motivational results there that I think will speak to most of you. And then, like Francesca, move into the C-star algebra realm and translate some notions and then give some examples. So that's the plan of the talk. So index theory is actually a branch of operator theory that takes a linear map, and first we try to do this on finite dimensional spaces, and we define the index as the dimension of the kernel of our given linear map minus the dimension of the co-kernel, which is the same as the kernel of the adjoint. Now, in finite dimensional linear algebra, we have a dimension theorem, and applying that, you see that actually, when you compute the index in this fashion, you will find just the difference of the dimensions of the domain and the codomain, seeing nothing about the map L. And so you've defined an invariant, which is not so good. It tells you not very much. In infinite dimensional space, the situation is quite different. We already saw the shift operator in Francesca's talk on L2 of n. In my talk, this operator is called S. Before it was called T. And if you compute the index of this operator, then you will quickly see that it's actually equal to -1. And that's because S star S is the identity, but SS star is not. And so there is a difference in the dimensions of the kernels. And this gives you a number that seems to depend on the operator. You could also say, in view of the previous result, this says that this is an instance where infinity minus infinity is equal to -1. There is something happening here, but it is a purely infinite dimensional phenomenon. I will set up the index theory for potentially unbounded operators, because these are the operators that arise in geometry. As I think we all know, typical geometrically defined operators are not bounded. They have a dense domain, and so that's why I'm setting it up like this. And we say that such an operator between two Hilbert spaces defined on a dense domain is Fredholm if it has closed range. Actually, this assumption is superfluous in the Hilbert space setting. And its kernel and the kernel of its adjoint are finite dimensional. So we basically put in the condition we need to define the invariant we want to define. A little cheap. But there's the first remarkable result is that the index so defined is invariant under taking homotopies, where homotopy should be interpreted as deforming the operators along a path in a, of course, relevant topology. This is a bit technical, I will not elaborate, but this, you can make sense of this. And if you have a path that stays entirely inside the space of these Fredholm operators, then the index actually doesn't change when you deform one Fredholm operator into another along a path of Fredholm operators. Now, this is remarkable because the separate quantities here, they will very likely change, but their difference is stable. So this is an observation that tells you that there is a potentially interesting invariant lurking here. Now, going a little deeper into this example of the shift operator, or shift type operators. On the circle, you can look at, under Fourier transform, the so-called Hardy space, which are functions that have only non-zero positive Fourier coefficients. And of course, that space is under Fourier transform, isomorphic to L2 of n. And there is an orthogonal projection operator, as there always is in Hilbert spaces. Now, if I take some function f in the circle algebra that we've seen in the previous talk, then we know that the circle algebra acts on this L2 space by multiplication, and as such it acts as a bounded operator, but it does not preserve this, this subspace. If f has itself sufficiently negative Fourier coefficients, then it will certainly map you out of that Hardy space. Also, the function fz is equal to z. Well, no, that's too quick, actually. So now what we do is we take this projection operator and we first multiply the function in the Hardy space by f, and then we project it back. Maybe the bracket should be here. And this gives us a map from H2 to H2. And if you do this construction to the function fz is z, then you find back this shift operator under the Fourier transform. That's where this sits. And then there is a very classical index theorem. So I would say it's probably the first index theorem in the sense that so the way I think of index theorems is they relate an operator theoretic and a topological invariant. And this index theorem does so. It was first proved by Fritz Noether, the brother of, and then later it was rediscovered by Goldberg and Krein. I think there was 1 or 2 decades in between these publications. And it's usually credited to the latter. And because both publications used quite different language at the time. Anyway, the theorem says that if I take a function on the circle that does not have 0 as a value, so it is invertible in a sense, then the associated tuplets operator is actually Fredholm in the Hardy space. So it has a finite dimensional kernel and a finite dimensional co-kernel, and its index is then equal to minus the winding number of this function. And the winding number is defined by looking at f as a function from the circle to itself by just dividing by its modulus, which you can do because it's invertible, doesn't hit 0. So such a function has a winding number, and the tuplets operator has an index. 2 are the same. And if f is sufficiently regular, so say C1, then you can actually even compute the winding number by an integral formula, as I've written over there. And this is a prototype of an index theorem, because first we relate an operator theoretic index to a topological object. And secondly, we compute this using some differential topology. And that's really the blueprint for what we want to do in non-commutative geometry as well.
Can I make a remark?
Yes.
You do it here for continuous functions on the symbol. The work of Goldberg and Goldberg-Krein extends this to also functions that may have jumps.
Oh, really?
There's a lot of material here.
Okay.
And perhaps while I'm mentioning this, it might be nice to mention to the audience here that Goldberg was actually a professor here at the Free University.
This I also
for a
did
long
not know.
time.
Okay, that's quite nice information. A lot of questions already pop up, like how do you do this for discontinuous functions? But maybe we should save that for later. But yeah, thanks for this this comment.
Do you think of this f as a trace of some nicer function
No, I don't.
on the circle or not?
No,
Can you, if
not
you
really.
can, but
It's a continuous functional circle.
Yeah,
That's all there is.
it's the symbol of the tuplet operator.
Sorry, to prove this, is this like, I mean, surprising the statement, but is what you do, like you take the function and then you auto standard function with this winding number and then you can read it.
That's one way of doing it. There are many proofs of this. There is a very simple K-theoretic proof, but you'd have to know K-theory. But I think there is an elementary proof using this idea. And you can, you can do probably a reduction to just the function fz is z, show that that index gives you -1, and then use some approximation using Fourier series. But by today's standards, I think there are elementary proofs of this fact.
The reason why I asked my question, because it looks like a property of the logarithmic of f of z.
Because of this logarithmic derivative here, yes. Yes.
The choice of z, of course.
Yeah. There must be some interpretation using this kind of idea, but I wouldn't be able to pull that out right now. Let me continue. So this can be not generalized. We will now look at the ingredients for index theory on manifolds. So I'm going to go slightly more abstract. And I fix a compact manifold and a pair of smooth vector bundles. I index them by plus and minus to distinguish them. And then I assume that I have a first order elliptic differential operator between these two vector bundles, where elliptic means that basically all derivatives occur. So this operator differentiates in all directions. And the first order means that locally you can express it in this kind of form. This is very roughly written, of course, but you have some functions and then some first order derivatives. And that's it. And I really want to look at just differential operator, not a pseudo differential operator, even though you can, this whole theory also goes into that direction. And then we say that such an operator is a Dirac type if d squared is a generalized Laplacian. I will say a bit more about that later, but in Francesca's talk, we saw already that on the torus, you can put these two derivations in a matrix off diagonally, and then when you square that matrix, you actually get the actual Laplacian. And that has to do with the flatness of the torus. I will show you a result that makes that slightly more precise in a minute. And then we want that for a smooth function, if we take the commutator of the multiplication operator associated to that function in these two spaces, then we get something called Clifford multiplication by the exterior derivative. Now this doesn't mean very much right now, but what you should think of is that we have a way on this space of sections to multiply a section by a differential form. And there are standard ways to realize this. So if I take any Riemannian manifold and I take the cotangent bundle, and then I take the even and odd exterior powers as vector bundles, then of course the sections of those are the even and odd degree differential forms. And I can put mapping between those the so-called Hodge-de Rham operator. So I take the exterior derivative and I add to that its formal adjoint. So I use the Riemannian metric and the Riemannian volume form to get an inner product, and then I can define a formal adjoint to the exterior derivative. If I add those two together, then I get an operator that maps between even and odd forms and has certain self-adjointness properties. And on this bundle of forms, there is a natural Clifford representation which comes from exterior multiplication by the form. So I'm writing df, but I could take any form here. and then subtracting the contraction by that form, which uses the Riemannian metric. Now, this is an example of a so-called Clifford representation, but this exists on any Riemannian manifold. So that's the kind of structure we look at. And again, the example we saw on the torus is a perfectly fine example of this. So I will, again, informally introduce more formal language. So this kind of structure that we have, this way to multiply differential sections by differential forms, that's what's called a Clifford module. And so a vector bundle is a Clifford module if its space of sections admits such a representation for multiplying by differential forms. And if I look at a connection, which takes sections of this bundle, or now I call it E, so my E should be S plus plus S minus. Sorry about this. And it takes it to the E-valued 1 forms. That's what a connection does in differential geometry. Then we say that this is compatible with the Clifford structure if when I take commutators of Clifford multiplication by a form, what I get is the Clifford multiplication of the Levi-Civita connection on the base manifold. So this relates two connections. It relates my upstairs connection to the God-given connection on the Riemannian manifold. So that's a condition. And it relates it to the Clifford multiplication in this way. Now, that's the general format for defining what's called a Dirac operator. And that takes this connection, you end up in the 1 forms, but now, because I have a way of multiplying 1 forms in sections, I can contract again using the Clifford multiplication. And that gives me an operator between the sections and itself. And this is a first order differential operator that we call a Dirac type operator. And there's a fundamental theorem about such operators, namely that if I have such a Clifford module and such a Clifford connection, and I look at the connection Laplacian, which is a standard generalization of a Laplacian that you can form once you have such a connection, then squaring this Dirac operator gives you the connection Laplacian, a multiple of the scalar curvature of the underlying manifold, and another curvature term, which is a curvature 2 form naturally associated to this nabla E. It's not literally the curvature, it's a slight modification. I want to mainly focus on the philosophy here. So what you get is, this is second order, this is second order, and this is 0th order, and it contains information about, a geometric information about the underlying manifold. So that's how one should look at this, this formula.
Can you go back 1 slide for
Yeah.
So C produces, given a 1 form, a section of your spinor bundle.
No, an operator on the sections of the spinor bundle.
Okay.
So what this does is, this is exterior multiplication by the form, and this is the contraction using the Riemannian metric by that form. So this maps an even form to an odd form by exterior multiplying this by the given form, and this maps it. So this maps it 1 degree up, this one maps it 1 degree down. But if you bundle it together like this, they operate between that. So they're operators, not sections. They're operators on sections. And that's why this works, because in this step, I have now, this is basically sections tensored with 1 forms. In this step, I contract the tensor product by multiplying by the 1 forms using this Clifford representation. That's why I can do this. So a connection maps you out of the space, the Clifford multiplication allows you to go back in. And if you do this for this non-commutative torus again, you get exactly these Pauli matrices, and what you recover in that case is exactly the operator that Francesca had. It's an example of this much more general framework.
And then you would have the 0 order.
Well, in that case, the torus is flat, so these terms are not there. Yes, that's the reason why she got exactly the Laplacian. In general, you get some extra stuff seeing the underlying geometry. And the point of this, since we're going to talk about non-commutative geometry, is that you can get your hands on this geometric information using purely operator theoretic methods. So these Dirac operators, yes, it's a scalar curvature. I didn't write that in the result, but that's the case, yes. So these Dirac operators, they see some curvature and some Laplacian. That's the philosophy. They also remember the Riemannian distance function.
Can I ask a question about the previous one?
Yes.
So it starts with that d bar or slash be a direct type operator, so that's given.
Yeah.
So given that operator, then I see the new thing is the omega e. So given delta, given d, you find omega e.
Yeah, you could say, okay, I have d, I of course have delta, and I have the scalar curvature. I can subtract them on this side. Then you find this form. But this form is also, it's independently given. You can construct it as a curvature form associated to that connection nabla e. So it's already there, and you can represent it. So this is a two form, and then the Clifford structure again allows you to represent this two form as an operator.
So all these things are then independently defined and happen to combine with this equation.
Yes, well, independently defined. Once you have this, then you have this, and the scalar curvature is of course already in the manifold. So it all comes from this. This is the fundamental object here. This Clifford connection. Yeah, so the other observation by Kohn is that this actually works for a large class of first order elliptic operators. But you have, of course, on a Riemannian manifold, the Riemannian distance. And if you just think of R, then you can recover the distance between 2 points by looking at this difference where F, this should just be, why did I write a G here? That should just be an F. Yeah, exactly. That's probably what happened when I was typing. So the G shouldn't be there. Well, I mean, it can be there. It does nothing to the supreme. It's allowed to be there. You look at functions basically whose derivative is less than or equal to 1. If you visualize this on the real line, and then you get the distance between 2 points, you get exactly by souping over the distance between different values of differentiable functions of derivative less than or equal to 1. You can just draw this for yourself. And this works on any manifold with a nice elliptic operator. So there's nothing about the Dirac type here that really matters. It's first order elliptic that matters in essence. And here, of course, we use the operator norm on the bounded operators on the L2 sections of the space. And again, the idea here is that the Riemannian distance function can be expressed purely in operator theoretic terms. Because the points we can view as so-called states on the algebra of functions, as Francesca explained. And the functions themselves, they act as bounded operators, and then there is this special differential operator that you single out. Now, I also want to emphasize at this point that non-commutative geometry is not about defining distance functions on C-star algebras or something. They're not there. We're just saying that once we have such an operator, we have something like a Riemannian manifold. And we just want to do Riemannian geometry in an operator theoretic language by working with that operator, not by constructing distance functions on the C-star. We forget about that because there may not be enough points to do this with. But this is a philosophical motivation for saying, okay, this operator is what's essential. It knows about the manifold. Now we want to pair these operators with vector bundles. So now there are going to be more operators and more vector bundles, and they play different roles. So suppose I am given one operator as before, one of these Dirac type operators in such a bundle S. And now I'm giving another vector bundle with another connection, just different data, another vector bundle with connection. I'm going to couple them. So I'm going to build another operator called one tensor nabla d plus that acts in the tensor product of these two bundles. For that, I need the connection because the operator d does not commute with multiplication by functions. We saw that the commutator was this Clifford multiplication by something. So it's not zero. So if I want to lift to the tensor product, this would not be enough, wouldn't be well defined. It turns out that to correct for the error, you need to add this term. This is a simple algebraic computation that can be very instructive. I will not do it, but we know then that Dirac type operators are themselves Fredholm. That actually also follows from this proposition. But if you take this twisted operator, then that turns out to be again of Dirac type, and it turns out to be Fredholm. So in particular, if I take no bundle here, then this result tells me that D plus itself was Fredholm. And so this is a way to take, on one hand, a vector bundle with a connection, on the other hand, one of these Dirac type operators, and I put them together and I construct a Fredholm operator. So that's the scheme here. And then we get to well, a landmark result of 20th century mathematics, the Atiyah-Singer theorem. And that tells us that given a Dirac type operator and such a vector bundle, if I take the index of the coupled operator, which by the previous proposition is well defined, then that index, which is an operator theoretically defined number, can be computed purely in topological terms. So on the right-hand side here, there is an integral of differential forms associated to the two bundles. Again, I'm not going to say what they are. It's that gets a little involved, but the idea is I have two bundles and I construct from them certain characteristic classes, and the index of the given Dirac type operator can then be computed as this integral, where again, the idea is that getting your hands on this number can be extremely hard, whereas this is generally computable. And it relates operator theory to topology. And now this notation here means that this, I want to view this as pairing a vector bundle with an operator and getting a number. So that was an observation of Atiyah in the wake of this result, that vector bundles and elliptic operators are somehow dual objects. And you can pair them and get numbers. And then you can compute these numbers using differential geometry. So just to see what you get when you take some concrete things, if I take this Hodge-Durham operator, which I have on any Riemannian manifold, then the index theorem actually recovers for me the Euler characteristic. So that's a fundamental topological invariant. And this can then be computed as the integral of the Pfaffian of the Riemannian curvature, which is the differential geometric side of this index theory. And of course, for a surface, this reduces to the Gauss-Bonnet theorem.
So what is, sorry, what is in the first example the vector bundle that you're twisting?
There's no twist here.
There's no twist.
So, oops, if you don't have to twist, so you can't. It's not necessary. So then you would get just the integral of what's called the A hat genus of the spinor bundle, and that's what you find there. But you could twist, and then you would find different invariants. You could twist by line bundles or something, and you would get other topological information.
Maybe explain this pairing idea, which is the Riemann block. So when we have a Riemann surface and it's line bundle.
Yeah, then
Maybe you could do the same thing with the ball.
yeah. No, so for Riemann Roch, you use the double, and if you add an extra vector bundle to this, now I must say that I think what the terms in Riemann Roch exactly are, but you get you recover really the Riemann Roch theorem by doing exactly that. So you twist the double by some line bundle.
So I mean the operator is of course is I was just thinking about the degree of these bundles, right? That you
you mean the divisor degree in this business, right? But the Riemann Roch picks up these degrees in the formula, and I think these are exactly, so if you take just the double and its index, or if you take the twisted double, then you pick up exactly the right terms in the index that give you the Riemann Roch theorem. So yeah, this is back to the pairing idea. So vector bundles pair with elliptic operators, and they give you integers. And these integers are topological invariants, but you compute them by geometric methods. That's what makes it computable. And now we can build from vector bundles a group by just taking direct sums of them and then formally adding inverses. So we just add the negatives. And we use some equivalence relation induced by basically isomorphism of vector bundles. Then we get what we call K0 of M. That's, at least in certain communities of mathematicians, quite a familiar construction. The dual group generated by the elliptic operators is called the K-homology group. And that's, I think, less familiar to most. But really, the objects of this group are really just these elliptic operators. They are an elliptic operator acting in a Hilbert space coming from some sections in some other bundle. And you can define an equivalence relation on these, basically coming from homotopy, as I indicated before. You can talk about homotopy of Fredholm operators in an appropriate topology, and one can use that to define this K-homology group. And then there is a pairing between these two groups, and it does exactly what I described before. And both groups are homotopy invariants, and this pairing is a homotopy invariant pair. And there is a Chern character on K-theory, which gives a rational isomorphism onto cohomology. Defining a Chern character on K-homology, landing in homology, is also possible, but it's much more involved, at least in the analytic model. So the history of this is that K-theory is a generalized cohomology theory, and by homotopy theoretic arguments, you can show that a dual homology theory must exist. But for a long time, the question was, can we find concrete models for this theory? And Atiyah and later Kasparov developed these models in the context of operator theory, which are somehow the computable models for this theory. So then you can think of the classical index theorems as computations inside this diagram, where you have the K-theory K-homology pairing, it's integral. You have the homology and cohomology pairing given by integration. It's real valued, and the the diagram commutes in some sense, and that's what index theorems do for you. They give ways to compute the values of these index pairings. Okay, I have until 1:45 more or less, right?
Yes.
Yeah, I just need to make sure that I'm not giving you too much material. So some things about Caesar algebras. We've seen these two theorems in a previous talk. So locally compact Hausdorff spaces are in one-one correspondence with commutative Caesar algebras, and vector bundles thereon are in one-one correspondence with projective modules. I will not elaborate on this much more because Francesca has given us an excellent exposition of this. Now, some examples of Caesar algebras. So the triplets algebra, we've already seen it. It's generated by the shift operator. It's non-commutative because the shift doesn't commute with its adjoint. If I have any discrete group, I can take the little L2 space on this group, and the elements of the group act as unitary operators just by the left regular representation on this little L2 space. That gives me a representation initially of the complex group ring. I can close up the image. I get what is called the reduced Caesar algebra of a discrete group. This object is defined for any group. And is a subject of study in various areas, at least related to non-commutative geometry. Cross products we saw. If I have an action of a group on a space, such as this irrational rotation that Francesca talked about, there is nothing special about that setting. You can have a group acting on any space, and you can construct a representation both of the group on L2 of X cross gamma. Let's assume the group is discrete, but this also works for topological groups. It's just slightly more involved. And the multiplication representation of C0 of X, they combine together, and because the group acts on the space, this generates a much smaller algebra than you would a priori expect. This is the cross product algebra. Then there is a fundamental result due to Riefel, which says that if the action of gamma on X is free and proper, then the functions on the quotient space, and this is in that case a nice locally compact Hausdorff space, is what's called Morita equivalent to this cross product algebra. I will not define what Morita equivalence is. I will just tell you that if two commutative algebras are Morita equivalent, they are actually isomorphic. So in the commutative world, there is nothing but isomorphism. In the non-commutative world, algebras can be Morita equivalent, whereas not being isomorphic. For example, the complex numbers is Morita equivalent to any Mn of C, any matrix algebra over it. They are the same object. So this relates to a question that was asked in the first hour. And under this equivalence relation, a point with the complex numbers correspond to a point, and any matrix algebra also corresponds to a point. In that sense, there is no extra information there. But this is an equivalence relation that says something about the categories of modules of these two algebras being actually equivalent in some sense. The main idea here is that if I have a non-free and proper action, this thing is not defined, but this thing is always defined. So for any group action, I can look at this thing and it replaces the quotient space in some precise way. Okay, here's the K-theory group of an algebra. It's formal differences of these finitely generated and projected modules. Same as the Grothendieck group of vector bundles. And now we come to Kahn's proposal of a non-commutative manifold. So we have Caesar algebra A, and we have a triple of data associated to A. The first one, this curly A, is a dense star subalgebra. So on a manifold, this would be smooth functions or C1 functions. There is some choice to make there. We have a Hilbert space which splits into two pieces, just like I had two vector bundles before. I now require my Hilbert space to consist of two bits that I know how to single out. And A is represented on each of them. So A acts on each of these Hilbert spaces. Then I have an operator, D plus D minus, where D minus is basically the adjoint of D plus. So I have one operator, D plus from H plus to H minus, and its adjoint. I put them in a matrix, and it acts between these Hilbert spaces. And I require that if I take 1 plus D squared inverse, this is some pseudo differential operator, but it's well defined. And then I multiply it with A, but let's just assume that A has a unit, and I can forget about this one. Let's just ignore this. I require that 1 plus D squared inverse is compact. This is the analog of ellipticity. So an operator that differentiates in all directions has the property that this 1 plus D squared inverse is a compact operator. I cannot talk about ellipticity because A is non-commutative. I have no points, I have no directions, but I have this, and it that encodes that property. And then there is my dense subalgebra that's singled out, and I require that the commutators with my unbounded operator, so they are a priori unbounded, but they are bounded. And this, if you look at differentiation on the torus or the circle, as we saw in the first talk, and you look at this commutator with a function, what you get is exactly multiplication by the derivative of that function. And that is bounded whenever the function is differentiable. So this data, it's a bit of a list. This is what we think of as the structure of a non-commutative manifold on a C-star algebra. So the C-star algebra is the topological space, and the Hilbert space and the operator give me the differentiable structure. And then by this Fredholm operator miracle business, we can look at equivalence classes of these structures, and that turns out to give us a group. Now this is not obvious. I can formally add these by taking direct sums. That's what you do in this group, like in the K-theory group. But you need to address inverses and so on. But this means that in the manifold world, we saw that this data, it knew some stuff about curvature, it knew some things about the Riemannian metric, and it also encodes a type of fundamental class in a certain cohomology theory. So once I have this data for a C-star algebra, there is some ground to say, okay, I am looking at something like a manifold. And for an actual manifold, I always have such a spectral triple by taking the Hodge-de-Rham operator. I just get it. So a manifold gives me this. There is another sort of deep result due to Kohn that says that if you have this, or this actually on a commutative algebra and a little more, then you can prove that there is actually that it is actually a manifold. But this is very hard, and I'm not sure how useful it is, in the sense that that's not really what you want to do. What you want to do is, okay, I want to think of this as a manifold. But there is a way back when you add some extra structure on these triples. And then you can do the same trick. So you can talk about connections on projective modules in a formal way. So they are maps from my projective module to this tensor product where omega 1D, once I have my operator D associated to my algebra, I can look at linear combinations of this form, and they actually behave like the differential one forms. So there was a question about the tangent bundle in the previous talk. In general, you cannot talk about derivations on the algebra, but once you have this structure, your replacement for the cotangent bundle is actually this subset of operators on your Hilbert space. Because if you look at the Dirac type setting, then this was commutator with a function. This was Clifford multiplication by the exterior derivative of the function. So in that case, you really recover the Clifford representation of the one forms. And then you can write down a Leibniz rule, and you can do all the things I showed you in a purely algebraic setting here. And you can do the index pairing because these operators turn out to then be Fredholm. And you get a pairing between the K-homology group generated by these operators and the K-theory group generated by the projective modules. I'm thinking about what to do. Maybe let's see, this is a lot of material. Or maybe I can just say something like this. So we have K-theory and K-homology, and this can be vastly generalized. I will not tell you the details of that, but you can actually define groups that take two C-star algebras as arguments, and this we should think then of as maps, generalized maps between two manifolds. And this was achieved by Kasparov in the late 70s and early 80s. So what he did was he takes two C-star algebras and constructs an abelian group. I'm not going to tell you how that works, but I can tell you the properties. If I insert in the first slot of this bifunctor the analog of a point, I get the K-theory group of the second algebra. If I insert the point in the second slot, I get this K-homology group generated by the elliptic operators. And there's a structure of a category which gives a composition rule.
K-homology or the star should be well.
No, this is what we call K-homology. That's that's in the literature. This is called K-homology, and that's because the functor from spaces to algebras is contravariant. Okay. So on spaces, this is a homology theory. K-theory on spaces is a generalized cohomology theory. And K-homology on spaces is actually generalized homology theory. But when we move to C-star algebras, this would be C of X. Okay. And X goes to C of X, is flips the arrows. It's just a terminology thing, but if you want to read about this, you have to look for this, because if you look for K cohomology, you will actually end up here. Yeah. Anyway, there's a composition rule which tells you that the elements of these groups are actually homotopy classes of generalized maps between these C-star algebras. And this recovers the index pairing. Now, one way to think of elements in this KK group is that they define a map from the K-theory of A to the K-theory of B using these rules here and this product. You see that that's what they do. Okay, and the last statement is not so.
Is there an analog for H? Is there something called an HH? Purely in topological context.
You mean bivariant cohomology theory?
Yeah, just ordinary homology that you can also combine.
Yeah, so there exist bivariant theories in cohomology. This has been done. And there is actually an analog in this world for algebras called cyclic cohomology, which then when you restrict it to commutative algebras, you get one of these bivariant homology theories. But there are also purely topological theories that have exactly this form. And they're called bivariant theories. Now, in the setting of manifolds, you can actually understand what's going on here a bit better. So if I have two manifolds, I can look at this group, so taking the functions on the manifold. And what then happens is an element in this group turns out to be given by such a diagram. So there is a third manifold in the middle, two maps come out of it, And there's some vector bundle here. I propose to ignore this for the moment because this doesn't play a very important role. What these KK groups encode is manifolds with two maps out of them. And this is what we call a correspondence. And Kohn and Skandali showed that this KK group, which was defined in operator theoretic language by Kasparov, can be described when you restrict to the topological subcategory by looking at such diagrams. And the composition rule given by this Kasparov product is just taking fiber products of these spaces in the middle. So you have two of these diagrams. Well, as I wrote here, ignore the vector bundles. You put them together by taking the product and identifying points that map to the same point in the middle manifold. So it's just a fiber product. That's what this product structure does. And that's saying that this elusive KK theory is given by homotopy classes of generalized smooth maps, where such a diagram would be considered a generalized smooth map. Because if I have a smooth map between manifolds, I can put it here and the other one here. So I can just put M in the middle and take the identity map here. If I have a map between manifolds, I get such an object. So in operator theory world, the cycles for this KK group are given by pairs where now everything becomes algebraic again, and it will look really similar to what we had before. We have a bimodule and we have some operator. It's always the same. There's Hilbert spaces and operators. Now there are bimodules and operators. And okay, there are some constraints. I will not give them to you. But in this operator theoretic world, you can think of this Kasparov product as this kind of coupling that we also saw in index theory. So what we have here is we have one differential operator and we have another differential operator. We take a product of these modules. I just take a tensor product, but that means that in the tensor product, I have two directions. And I want to, again, get something that differentiates in all directions. So I put together the operators. Well, the first one is easy. The second one, I have the same problem that I had before, that I cannot just take the tensor product because there is this non-commutation going on. So I had to put in this connection to correct. It's exactly the same here. And this is the way to think about the Kasparov product in a geometric way. This is not how Kasparov originally defined it. He used a different picture where a lot of functional analysis was needed. Here, still some is needed. I'm not saying this is necessarily easier, but at least I can give you a formula. In the original approach, there is no such formula. It's just an existence and uniqueness type of statement. So both objects now, so manifolds become a C-star algebra, Hilbert space and an operator, but also maps become a bimodule and an operator. So the language is fairly uniform. And to go to some examples before I get to the end without going too much over time, let's look at something concretely geometric. So we take the classical Hopf fibration. We have a three sphere and the circle as one acts on this three sphere. You can embed it in the quaternions, and then the one sphere is the one sphere of complex numbers. We can multiply elements in the three sphere, these unit quaternions, by unit complex numbers. We take a quotient, we get the two sphere, and there is a Peter Weil decomposition of the smooth functions on the three sphere. It looks like this. So the smooth functions decompose as a certain completed direct sum of sections of various line bundles on the two sphere. On this, on using this decomposition, you get all these degrees, and now you can basically look at the Fourier transform of the differentiation on the circle in the setting by just multiplying a section of this nth line bundle by the number n. So I have just put in the spectrum here as such. And this commutes with left multiplication by elements in S2. So in my KK-theory elements, I said I have a bi-module. Well, I can multiply from the left by functions on S3 because this is CS3, and from the right by functions on S2 because I have this fibration map going between them. And there is this, this unbounded Fourier transform of a differential type operator. This pair then defines such an element in this analytic group. And there is a Dirac operator on S3. It's just the geometrically defined Dirac operator. And similarly, there is one on S2. And they define the two spectral triples on these two spaces. And now, in fact, you can show that this Hopf fibration induces a decomposition of the Dirac operator on S3 using the Dirac operator on S2 and this vertical operator that differentiates in the circle action direction. And again, a curvature term shows up. This is in homotopy land. This is not important, but it is again encoding some curvature coming from this vibration. And so, what have I done here, or what am I trying to achieve conceptually? Is I have a Hopf vibration between these two spaces, and I have encoded that in operator theoretic language by such an element that represents something in a KK group. Now, maybe I can just go through this, but not focus too much on the details. Sketch something about solid states physics before we call it a day. So, in solid states physics, we think of atoms in some lattice. This lattice, of course, you could take Z2 in R2. That's highly symmetric. Its quotient torus. And as Francesca said, you can look at vector bundles on this torus, and this is how physicists initially described such systems with some success, and even there some non-commutative geometry comes in. But of course, a more realistic model is if these points on the lattice are really quite disordered. You don't know where the atoms exactly are. They wouldn't be sitting in this kind of very nice configuration with a group structure and so on. So that's what is described on this slide. I don't want to elaborate too much. You can, from such a disordered point set, you can construct an algebraic object called a groupoid. So it's not a group, but it's something more general. And to that, you can associate a C-star algebra. And then there is all kinds of physical input coming from magnetic fields and so on. And what the important observation is that the Hamiltonians of your physical system, so these are what describe the physics of the system, they turn out, so you want them to have certain invariance, you want some translation invariance and some time symmetry and so on. They turn out to define always elements in this specific C-star algebra, which is always non-commutative. So it's always non-commutative, and the relevant physical operators are living in there. That's what this proposition says. And then you need some extra assumption, and that's the topological assumption on the system, that this Hamiltonian needs to have a spectral gap. And if it does so, then it defines a K-theory class. If you have this K-theory class, you can pair it with some naturally defined KK element coming from position operator. So it again comes from some unbounded operator, and you have some integral. And this means that the Hamiltonian gives you some numerical invariance. And they are defined really in this C-star algebra language. There's no other way to describe them other than, of course, completely directly, which is what the physicists do. But mathematically, this is what's going on. And well, this, I make it more explicit here. Let's not go into that too much. If I have this material, or maybe it's three-dimensional, so I have points coming in here, and I have a boundary in the material. So that's what this theory of topological insulators is about. Is I have a material, it's insulating in the interior, and it's conducting on the boundary. And it turns out that so you can measure currents on the boundary, and they correspond to states in the interior. There are two such groupoid algebras here. This is the big one corresponding to the bulk, and this is the smaller one corresponding to the edge of the material. And the bulk boundary correspondence in physics says that any invariant in the bulk has a corresponding invariant in the edge. Now, what one does here is by introducing the edge, you have a specific direction. So maybe you have three directions. The edge is one of them. So I have a position operator going into, for each direction, I have a position operator. And this means that my Dirac type operator differentiates in three directions. But when I introduce the boundary, I forget one of them. And that can be encoded exactly in this operator theoretic language of this Kasparov theory that I sketched. And it can be implemented by a Kasparov product, giving a map between the K-theory of the bulk and the K-theory of the edge. And then if you compute the invariance, you get a commutative diagram. And this bulk boundary correspondence can thus be completely understood in terms of this language of C-star algebras and KK-theory, which is defined in terms of operators. So that was probably a bit fast, but let me wrap up. So vector bundles pair with Fredholm operators. This is what gives you index theory. This is really the main philosophy. And the index theorems relate K-theory to cohomology. Then if you want to go non-commutative, you have to forget all your geometry. You have to make everything operator theoretic. When you do that, you get what's called KK theory. And this allows you to do computations in the non-commutative setting. The relevant algebraic structure in Kasparov theory can then be explicitly described by generalizing all the geometric input to this operator theoretic setting. And then you can think of, well, I gave you the Hopf vibration, but that idea works for any principal bundle. If I have a principal G bundle and a Dirac operator, then I can always factorize it into a bit that comes from the group action direction and a bit that comes from the geometry of the base. And the bulk boundary correspondence in physics, which I went over really quickly, is an example of this idea. You just factorize the relevant operator that encodes your physical system into an edge direction and the remaining directions that you have in the bulk. And this allows you to interpret the fact that these invariants in physics correspond to each other as something existing in this K-theoretic, this operator K-theoretic setup. So that was quite a lot, I guess. I thank you for your attention.
Are there any questions, remarks, either in this room or in the room, in the lodge?
So can you show us the slide about the Hopf vibration again?
Yes.
And maybe because I thought, oh, Hopf vibration, I should understand this, and I still think I managed to get it. Right? So this is what you like what you refer to as factorization of.
Yes. So
right?
this is the setup. So I have the Hopf vibration. I get this module, and I get this operator which only knows something about the group action. So here I use, for this decomposition, this comes from the invariant.
Because you said something about you take the completion, because on the one hand you have the smooth functions on S3, and on the other hand you have sections of these line bundles of S2.
And then you mean here? I didn't say, did I say? Oh, here after appropriate. Yeah, so you need to do something here. which just means that I want to complete this in a kind of an L2 way in this vertical direction, but not in the S2 direction. So I want to introduce some L2 decay in this direct sum. It's an analytic subtlety. I'm not sure if we really need to think about this now. If we just think about this, so we can deposit smooth functions, and we have this operator, and it respects this decomposition. So it maps each bit to itself. It just multiplies by bigger and bigger numbers. And it's really the Fourier transform of the operator that differentiates in the circle direction. So only in the direction of the group action that we have. And then you can ask, okay, the Dirac operator that I would have here, how is it related to this this other differential operator that I obviously get here that differentiates in the direction of a group? Well, it turns out that it works in this way. So I have my Dirac operator on the 3-sphere. This S tensor 1 is coming from this here. So that's my differentiation in the circle direction. I have a natural Dirac operator, and now you can ask, okay, what's the difference between them? What's left? Well, what's left is exactly the lift of the Dirac operator on the 2-sphere through some connection. So I need to choose, or there's actually a natural connection in each of these line bundles. So the connection acts in each degree as well. And so I can lift the Dirac operator on S2 to this section space in each degree separately in the way that I indicated before. So this is just this twisting construction. So I get an infinite family, if you will, of lifts of the Dirac operator on the base through each of these line bundles. That's what this thing here is. And then I say, okay, I add them. What I get is almost what I'm looking for, but there is a curvature error, which tells me something about the underlying geometry. And this is, in some sense, a prototype of what always happens. So, of course, this is a very nice vibration because there is a group action in the fibers. But if I have an abstract vibration of two compact Riemannian manifolds, you can get a similar formula. But it's a little more implicit, the terms that you get in the formula, because you don't have this extremely nice geometry that you have here. But the idea is all the ideas are visible in this example.
Thank you.
Thanks. Are there any other questions? Okay, let's thank you again. Stop the recording.